In this video, we will use linear modeling to predict how a boat rocks from side to side in the water around its flat equilibrium position. In the previous video, we saw that we could describe this rocking motion using the rotation angle of the boat, theta, which is a function of time, t. Recall that we define theta to be the angle between this flat waterline and this line that rotates with the boat. We use the convention that theta is positive when the boat is rotated clockwise, and that theta is negative when the boat is rotated counterclockwise. We also saw that when the boat is sitting flat in the water at theta equals 0, it is in an equilibrium position. So how do we determine the function theta of t? Well, we know that the motion of the boat is governed by Newton's second law. Recall that for linear motion, Newton's second law says that the mass, m, times acceleration, x double dot, of an object is equal to the force F applied to that object. However, we are interested in the rotational motion of the boat, and so we need to use the rotational form of Newton's second law. This states that the moment of inertia, I, times the angular acceleration, theta double dot, of an object is equal to the torque, tau, applied to that object. Note that the moment of inertia is the rotational analog of mass, and so the larger the moment of inertia of an object is, the harder it will be to rotate. Similarly, the torque is the rotational analog of force, and so if you apply a larger torque to an object, you will cause a greater angular acceleration. We now have a second-order differential equation whose solution is theta of t. For a given boat, the moment of inertia will be a constant. However, the torque will be a function of theta. Therefore, before we can solve this differential equation, we need to figure out how the torque depends on theta. To do this, let's recall our observations of the rocking boat in the previous video. We saw that when the boat was sitting at theta equals 0 in its equilibrium position, it just sat there and did not rotate. So, the angular acceleration of the boat is 0, and Newton's second law then tells us that the torque, when theta equals 0, is equal to 0. So, if I draw a graph of the torque versus theta, this tells us that the torque must pass through the origin of this graph. We also observed that our boat had a stable equilibrium. This was because when the boat was rocking in the water, we observed that the water around the boat acted like a spring. For positive rotation angles, the boat experienced a negative torque, acting to rotate the boat back towards its equilibrium position. So, on this graph, it means that the torque passes through the bottom right quadrant. Similarly, we observed that for negative rotation angles, the boat experienced a positive torque. Again, acting to rotate the boat back towards its equilibrium position. So, we also know on this plot that the torque passes through the top left quadrant. In general, the torque will be a nonlinear function of theta, and it might look like this, for example. However, we are mostly interested in the boat's behavior around its equilibrium of theta equals 0. Therefore, all we really care about is how the torque behaves for small rotation angles around this equilibrium. Therefore, we can approximate this nonlinear function using a tangent line at theta equals 0. This gives a linear approximation for the torque of negative k times theta. K is a positive constant such that negative k is the slope of this tangent line. Remember that this linear approximation is only valid for small rotation angles. We can now plug this linear approximation back into our second-order differential equation we obtained using Newton's second law. This gives I theta double dot plus k theta equals 0. You will recognize that this is the equation of a simple harmonic oscillator. And so we know that it yields oscillatory solutions around theta equals 0. We also know that the period p of these oscillations is equal to 2 pi divided by the square root of k over I. I should point out that if in the future we wanted to perform a more detailed analysis of the system, we should include a damping term in this equation. This is because we observed in the previous video that when the boat was rocking, the amplitude of the boat's oscillations decayed over time. However, for this video, we will neglect the effects of damping and just concentrate on this simpler equation, as it still describes the motion of the boat very well. Up until this point, we have been considering a boat that has a stable equilibrium. However, this will not always be the case, because we will later see that the shape of the boat dictates whether the boat has a stable or unstable equilibrium. In the case of an unstable equilibrium, the torque near the equilibrium will have a positive slope instead of a negative slope. This positive slope will mean that this negative sign becomes a positive sign. And so this positive sign becomes a negative sign, giving the equation I theta double dot minus k theta equals 0. This differential equation yields very different solutions. For example, consider the initial conditions. Theta at time t equals 0 equals 0, and theta dot at time t equals 0 equals some constant c. These initial conditions correspond to the boat starting flat in the water, but with some initial angular velocity. For example, if you gave the boat a slight kick. I now invite you to pause the video and try and solve this differential equation with these initial conditions.